I imagine that right now you are feeling a bit like Alice, tumbling down that rabbit hole. I can see it in your eyes. You have the look of a man who accepts what he sees because he expects to wake up. Ironically, this is not far from the truth. Let me tell you why you are here. You are here because you know something. What you know, you cannot explain. But you feel it. You've felt it your entire life. There's something wrong with the world. You don't know what it is, but it is there. Like a splinter in your mind, driving you mad. It is this feeling that has brought you to me. Do you know what I'm talking about? Do you want to know what it is? It is all around us, even in this room. It is a world that has been pulled over your eyes, blinding you from the truth. Unfortunately, nobody can be told what the Fourier Transform is. You simply have to experience it for yourself.
This is your last chance. After this, there is no turning back. You take the blue pill, the story ends. You wake up in your bed and believe whatever you want to. You take the red pill, you stay in Wonderland, and I show you how deep the rabbit hole goes.
Okay, all I really had were gummies. And Sour Patch Kids, I guess. And yeah, I wish I had some nice round glasses, but all I had were these weirdo ones that are like leopard print. These were my wife's, and she doesn't even like leopard print. Who knew? Anyway, yeah. So what I'm going to talk to you about today is the Fourier Transform. This is for my class, Data-Driven Methods in Dynamical Systems. And last time we talked about the discrete Fourier transform and how it can be used as a time grapher, and we analyzed the accuracy of the swatch, which seemed to be just quite a bit slow. Actually, I noticed the other day that it was actually 4 minutes slow after I hadn't really set it for a few days. So what I'm going to talk to you today is about the Fourier transform and where it comes from, how it's defined, and let me tell you, it is not an integral. It never is an integral. Okay, it's sometimes an integral, but in like 5 functions. I just told you that the Fourier transform is not an integral, but every time you've seen it it's written as an integral. You have, say, the integral from negative infinity to infinity of f of x times e to the minus I 2 pi x times k, integral taken dx. Right, and this is supposed to be the Fourier transform of f at k. Sometimes we write that as a curly f of f evaluated at k. Other times we write it as f hat at k, but always it's given to you as an integral. And the integration actually works out sometimes. If f is, say, a Gaussian, then that is a proper integral. In fact, the Fourier transform of a Gaussian is, in fact, another Gaussian. But that isn't actually always going to work out. There are cases where we want the Fourier transform of a function, but that integral doesn't even exist, just by simple Calc 2 reasoning. So for instance, if I want to take the Fourier transform of sine of x, that integral has the integrand of sine of x on the inside times a complex exponential that has magnitude 1. So you can take the absolute value of the inside, it doesn't go to 0. And we are told in Calculus 2, when that doesn't happen, then that means that the integral doesn't exist by the, what do you call it, the limit test. But on the other hand, sine is supposed to be the quintessential object that you take a Fourier transform of. It's supposed to give you a 1 Hertz frequency. So what gives? That integral doesn't exist. And then we have even crazier things. Things like what we call the delta function. Sometimes the delta function's Fourier transform is written as the integral from negative infinity to infinity of delta of x times e to the minus I 2 pi kx dx. And then we just say that Fourier transform is the function 1. That's a bit confusing. That was written as an integral, right? And we're told that when we integrate against a delta function that that's just going to be the same as evaluating the other function at 0. Because delta function is supposed to be 0 everywhere else and then infinitely large at the origin. In some abstract sense, that's supposed to produce a value, even though there is 0 width to that chunk. So in all of these respects, that's not actually a proper integral, this Fourier transform. And so what I'd like to tell you is what the Fourier transform is, And this involves things called functionals and my field called functional analysis. And we're also going to be talking about some sort of function space. And this is a collection of functions that are very special to us. And in this case, we'll talk about the Schwartz space, although sometimes you can also talk about the space of compactly supported, continuously, infinitely differentiable functions. But the Schwartz space is a little bit easier to talk about. And then this will allow us to define what is called this abuse of notation. And mathematicians do this stuff all the time, and they use it to disguise things that are just a little bit uncomfortable. And that's exactly what these integrals are. They're an abuse. And what I would like to do is I would like to explain this abuse of mathematics and why we're okay with talking about the integral in this fashion. And this will also clear up some things, like the connection between the discrete Fourier transform and the Fourier transform itself, where we can actually get from one to the other and still be in this family of things that we call the Fourier transform. This is in contrast to what you see in Stephen Brunton's excellent series on the Fourier transform, and basically a lot of the same things I'm talking about here, where he says that the discrete Fourier transform should really be called the discrete Fourier series. But I want to tell you that Fourier series and Fourier transforms are actually one and the same. But again, it falls underneath this abuse of notation, this abuse of mathematics. Horrible. Let's go ahead and talk about the first item, and that is functionals. So one of these early things that you hear about in, say, undergraduate mathematics, or if you took like a signal processing class or something like that in undergrad, what you've learned about is this thing called the delta function. And the one thing you know is that it's not a function. That seems to be the first thing that everybody tells everybody else. But even mathematicians who come out of undergraduate, I mean, even though they'll declare to their engineering comrades that the delta function is not a function, you can't treat it like a function, etc., they'd be hard pressed to tell you what it actually is. And I'm going to tell you, the delta function is a functional. It used to be called a generalized function back in the early 20th century, but that sort of language has sort of vanished over the past, say, 30 years. So what is a functional? So first, if you're going to talk about functional, you need a space of functions. A functional acts on functions. And so we're going to start by talking about the space that we call the Schwartz space. The Schwartz space consists of functions that are infinitely differentiable, and they are what we call rapidly decreasing. And that means that if you take a polynomial and you multiply it by this function, the absolute value of this function is going to go to 0 as you go to negative and positive infinity. What's more is that every derivative has that same property. So if you take 20 derivatives and you multiply it by a polynomial, again goes to 0. And so it's extremely, extremely flat as you go off to infinity, flat to 0. But it's also infinitely differentiable, which means that we can do derivatives and all these other nice things to it. Now, what's really nice about this rapid decreasing property is that we can do all these things that you have to usually watch out for in mathematics, and we can do it without even thinking. So things like exchanging integrals and things like that. All of that will always work on the Schwartz space functions. So that makes them a really nice realm to do mathematics and mathematical analysis. And there's also, they have a topology on them, and this topologies define what it means for one object to converge to another one. And in this case, their topology is defined by an actual metric. Basically, if you take a look at, say, phi, then you say that the sequence phi n out of the Schwartz space converges to a function phi if the supremum norm over the entire real line converges to that other phi. So if you take the absolute value, the maximum of the absolute value of the difference between phi of x sub n minus phi of x, then that goes to 0. And then you can take a look at, say, the derivatives, and that has to go to 0 too. And then you take the derivatives times a monomial, and then that has to go to 0 as well. And if all of those things work out, then you say that phi n converges to phi in the Schwartz space. And you can actually spin that out into a nice metric, so you don't have to keep saying all this crazy stuff as you keep working. And so now we have some way of talking about a sequence of these functions converging to a sequence of the other functions. And this is in terms of something you're probably already familiar with, which is the convergence of two continuous functions over, say, the real line, or two bounded continuous functions over the real line. Now, the next thing we want to talk about is a functional. A functional is something that takes a member of a function space to scalars. So it takes, so in this case, if we take a look at the delta function, when the delta function acts on, say, a Schwartz space function, what it ends up giving you is the evaluation of that function at the origin. And so this it's an operation that takes you from a Schwartz space function to the evaluation of that function at the origin. That is called a functional. Now we say a functional is continuous if when you have convergence in the Schwartz space and you hit that sequence with the functional itself, we'll call that functional, say, t. Then t of phi n is a sequence of real numbers, and if that converges to another real number that is represented by t of phi, then we say that the functional t is a continuous functional on the Schwartz space, provided that happens to every sequence that converges inside the Schwartz space. The space of functionals is typically called the tempered distributions. Tempered distributions, they get their name from probability distributions and some connections with measure theory, but we don't really need to know about that. We just need to know about them as being functionals. Now, there's this very special class of functionals, and these are called regular functionals. And we call them regular because there's a function that represents them. So for instance, if you take some other function f, I will say that this is a symbol of a tempered distribution, of a regular tempered distribution. If you can write the tempered distribution acting on a Schwartz space function phi as the integral from negative infinity to infinity of f of x times phi of x dx. We will call this the functional, the regular functional corresponding to the function f. And it's through this that we'll figure out ways of applying all sorts of different operations to functionals. And I've already done a video talking about operations that you can do to functionals, but we'll just stick to the Fourier transform right now. If we want to define the Fourier transform on a tempered distribution, we first look at the special tempered distributions that are regular. And so if I take a function f that I want to throw into a regular tempered distribution, then I basically, I can also look at another function where I take f hat. And if I put f hat as a symbol of a regular tempered distribution, and then I go ahead and I write it out as this integral from negative infinity to infinity of f hat of x times phi of x. And we can choose f to be something like in the Schwartz space, something where we know that we're going to get a proper function out of the Fourier transform. And we're not only getting a proper function, but it can be represented as an integral, a real integral, proper integral. We haven't left integration yet. And so then what you can do is you can do an exchange of integrals, and you can move the Fourier transform off of f and put it on phi. And then this will give you a new functional on phi. But it ends up being a chain of things. So if you want to talk about the Fourier transform of the regular tempered distribution corresponding to f, then what we can do is we can just take a look at the tempered distribution corresponding to the Fourier transform of f. And that can be written as follows. So we can rewrite the tempered distribution corresponding to the function f hat, and this acting on phi is written exactly as the tempered distribution corresponding to f acting on the Fourier transform of phi. And these two quantities are exactly the same. And so now, instead of just talking about regular distributions, we can define a Fourier transform on all tempered distributions. And all we do there is that before we apply the tempered distribution, we apply the tempered distribution to the Fourier transform of the function we care about. And ta-da, that is how we define the Fourier transform of a tempered distribution. And this isn't actually even an integral. This is a chain of operations that happen on the Schwartz space, and yeah. But we like the notation so much of the Fourier transform, and it actually ends up not hurting us too bad when we think of it this way, that we're going to take the integral representation of the Fourier transform, and we're just going to say that that this is what the Fourier transform is of the tempered distribution. But anytime we put a tempered distribution inside that integral, what we're really saying is the thing I just said before, whereas the tempered distribution applied to the Fourier transform of the Schwartz space function. And so that's the definition. But how do we get from the Fourier transform to Fourier series? That is a lot trickier. And so we're gonna have to go back and we're gonna have to talk about convergence of tempered distribution, of sequence of tempered distributions. And then from there, we can string it all together using periodicity of a function. And so, so hang in there. Try and figure out the most concise way of putting all this. So first of all, we need to talk about a topology on tempered distributions, because you can't talk about convergence without a topology. Now for the Schwartz space, I told you that that can be defined in terms of a distance function. And so this means that it was a metrizable topology. But on the space of tempered distributions, or the space of functionals, it's not quite as straightforward to define a topology. I mean, it's actually not that bad of a topology, but it's not metrizable. And so the only way you can really evaluate if you're going to be converging is not through a collection of real numbers, but you actually have to look at a sequence of tempered distributions applied to a particular Schwartz space function, or rather applied to all the Schwartz space functions. And so, and this is what is called the weak topology on tempered distributions. And so let's go ahead and talk about what it means for two tempered distribution, a sequence of tempered distributions to converge to a tempered distribution. So basically what we're going to do is say we have a sequence of tempered distributions. And so for instance, this could be a collection of delta functions, each one centered at, say, xn, and say xn is approaching the origin. Then you would think naturally that the sequence of delta functions should be converging to the delta function centered at 0. And you'd be right. But how do you determine that? Well, basically what you do is you take this sequence of tempered distributions and you apply it to say an arbitrary element out of your Schwartz space. Then this is going to give you a sequence of real numbers, just like what we saw before. And then basically you're going to see that for the Schwartz space function evaluated at xn, we know that that converges to the Schwartz space function at the origin, since xn goes to the origin, and the Schwartz space functions are continuous. That means that that function on the right-hand side, being the evaluation of the Schwartz space function at the origin, is going to be the limit of these tempered distributions. And so that's how you define convergence. Basically what you do is you take a sequence out of your tempered distribution, and then basically that sequence of tempered distributions, when you apply them to any Schwartz space function, the result has to converge to the tempered distribution on the other side that you want to converge to. And if that happens, then ta-da, that is convergence, and you've just defined your topology. This is the topology of pointwise convergence. And so, and this is how we're going to define the series that comes out of this thing that's not an integral. Hey, Joel from the future, and I wanted to stop myself before I missed this great opportunity to tell you the really slick argument that gets us from the Fourier Transform to Fourier Series for periodic functions. Let me make sure my microphone's on. There we go. Okay, so we're going to need two ideas. The first idea is that whenever you have a delta function centered at a certain point, so this is a shifted delta function, if you multiply that tempered distribution by some proper function, the ultimate result is a new tempered distribution that is that same delta function, just multiplied by the function evaluated at a very particular point, which is where that delta function was centered at. And the other idea is the Poisson summation formula. And now this relates the sum of integer samples of a function to the sum of integer samples of its Fourier transform. And this is going to allow us to change a bi-infinite series of delta functions to a bi-infinite series of exponentials, and back and forth. And so, and where the series, both series are interpreted as converging in terms of tempered distributions. Okay, that said, let's talk about the Fourier transform of a periodic function. Now, I already told you exactly how we can define that. That's by using these regular tempered distributions. But what we want to do next is we want to move from that to a Fourier series. And you do that the only way you really know how. You split the function up in terms of its periods. Now, this isn't going to be like a strictly like integral separation, because truly this is a tempered distribution we're talking about, but it turns out that this operation is perfectly valid. And so what we're going to do is we're going to split this into each of one of its intervals, so it will index by s. So we're looking at these intervals from s times t up to s plus 1 times t. And so I split the integral representing the Fourier transform, which we know is not truly an integral, but this is okay. And so we write this as a bi-infinite sum. Now, what we end up having is we have now the integral from s times t up to s plus 1 times t of f of x times e to the minus I 2 pi k x, and this integral taken dx. So this is a function of k. And I'm going to use a u substitution, and I'm going to use the u substitution of u is equal to x minus s times t, where t is the period of our function. Now, what happens here is now we've shifted all these integrals to going back to being just going from 0 to t. And now f, we replace x with u plus st, and that is really just f of u. Now the x gets replaced by u plus st inside the exponential, but we can just peel off a piece of that and take it outside the integral. And so now what you're left with is a bi-infinite series of this integral, and it's the same integral every single term, that is a function of k, and now this times some complex exponential. We can take that integral term and we can factor it all the way out. And this is a function of k, we'll write it as p of k, and now this is multiplied by a bi-infinite series of exponentials. So we can use that Poisson summation formula to change this to a bi-infinite series of delta functions and multiply through that function pk back. Now, that function pk is going to be evaluated at each of the centers of these new delta functions that we looked at. And so, so now we can have just a single real number there next to these delta functions. And so at the end of the day, what we see is that the Fourier transform of a periodic function is the same as a series of impulses times some real number. And what we can do then is we can use the inverse Fourier transform, which recovers the original function back from the Fourier transform itself, and then you end up getting a Fourier series for that periodic function. And I think this is the coolest thing in the world, and this is really a strength of functional analysis. Now, I think this is a good place to stop. I've just shown you how to get from the Fourier transform all the way down to Fourier series in all of like 20 minutes. And so before I really overload you, as if I haven't already, let's stop here. So thank you for traveling down this rabbit hole with me and taking that red pill. And please subscribe, ring that bell if you want to see more content like this, or even if you don't want to see more content like this, please feel free to subscribe. And next time, I think we're going to cover the Nyquist theorem, and then after that, we'll take a look at things like vuvuzelas and Stalker. But for now, I think it's time to go. Thank you for watching, and I'll see you next time.